Right. One of the most important topics in probability, or one of the most important and recurring assumptions that we come across in probability is the independence assumption, and exchangeability assumption. Those are two different things, and we're going to talk about them right now. So independence and exchangeability. Okay. In the Craps model, we assumed, without really saying it, because we hadn't introduced it yet, but we made an implicit assumption that the roles were independent. And what does that mean? Definition. Two events, A and B, are independent. There's a few different ways to define independence. They're all equivalent, but they're independent if the probability of A intersect B is equal to the probability of A times the probability of B. Product of the probabilities. Some observations is that drawing with replacement from the same set usually, not always, usually assumes that the draws are independent. So we made this assumption implicitly without saying it. We made this in the birthday problem. We made it in the craps problem. We're rolling the dice repeatedly. We're rolling the dice repeatedly. We're assuming that the second roll is identical to the first, right? That the first roll, in a statistical sense or probabilistic sense, and in particular that whatever happens on the first roll does not affect what happens on the second roll, and so on. Very important assumption. We made that assumption here when we said that, well, we're aiming for a point of 4, and then we observe that the second roll was neither a 4 or a 7. We assume that doesn't affect the outcome of the third roll. So the third roll is identical in some sense to every other roll. And that's what allowed us to set up this recursion, and that's what allowed us to solve the problem. Okay. Draws that are uniformly done without replacement produces an exchangeable observations. What does that mean? Exchangeable observations are not independent, but they have a symmetry to them. Okay, so let's talk about an example. So a good example, I'm gonna go through a simple example here, then we'll go through a more involved example. So rolling dice is a good example, or lottery, drawing balls out of a box with replacement. No, I'm sorry. A lottery is a good example of drawing without replacement. So that would be an exchangeable situation. Rolling dice, good example of sampling with replacement. Craps. Poker hands, when we calculate probability of poker hands, that would be drawing without replacement, in the sense that when I deal you a 5-card hand, I deal your first card, your second card comes from the rest. You don't put that card back. Obviously, you have 5 distinct cards. So let's just write some examples. Craps, roulette are draws with replacement, right? Each spin of the roulette wheel, we're spinning the same wheel. Poker, lottery are draws without replacement. So they have kind of slightly different dynamics and different assumptions that we have to account for. Let's suppose 2 balls are drawn from a box. The box has 6 numbers, 1 up through 6, and they're drawn without replacement. What's the probability that the first ball is a 2? We know how to do this, right? We're going to draw 2 balls. Probably that the first ball is a 2 and the second ball is anything, right? We know the multiplication rule, right? How many possibilities are for the first ball? 1, because it has to be a 2. And then once we observe the second, once we observe the first ball being a 2, how many possibilities are for the second ball? 5. And how many total possibilities are there? Well, these are 2 permutations of 6, right? So this is a 2 permutation of 6. Remember, we are picking 2 balls in order out of 6. The number is 6 fall 2. 6 times 5, 1/6. What's probably the second ball is a 2, and we ignore the first ball? Well, in this case, second ball has to be a 2, first ball can be anything, but it's the same calculation. Second ball, we think about the second ball first. First ball, 6 fall 2, 1/6. What's probability that the first ball is a 2, given that the second ball is a 1? Well, in this case, what's probability that we have to say, well, what's the probability that we have 2, 1, right? It's probably that both occur. Well, in this case, it's 1/30, right? Divided by probably the second ball is a 1. We already did that because the probability the second ball is a 1 is the same as the probability the second ball is a 2. It's 1/6. So this is 1/5. Okay. So in general, what does this tell us? So in general, if we draw without replacement n times, little n times from a set for any distinct indices n1 up through nk. So we subset our attention. In this case, we drew twice without replacement, and then we subset our attention to only the second index. Well, in this case, the first index, in this case, the second index. The chances associated, so the probabilities associated with draws n1 through nk are the same as the probabilities associated with the first k draws. So in other words, and this is where we say the draws are called exchangeable. Okay, so when we have exchangeable observations, I can ask you, let's say that we were going to draw 200 things. We have a box of 1,000 numbers, and I'm going to draw 200 times, and I want to know the probability that the 151st draw is the three ball. Well, it sounds pretty complicated at first because you're saying, well, I have to account for, well, the first ball can be anything, the second ball can be anything, I can go up, and then I have to get all the way to the 151st ball of that being exactly three. Well, well, that's one way to do it, and that's going to be pretty hard to do, and it's going to take you a long time to figure that one out. But by realizing that we're drawing without replacement and that it's uniformly without replacement, gives us an exchangeable sequence, then asking you about the chance that the 151st ball is a three has the same probability. It's the same as the first ball being three. And that's easy to calculate because we just have to ask, well, if I only draw once, what's the chance that I get a three on the first pick? In this case, if I had 1,000 balls, 1 over 1,000. Okay. So what's an example of where this comes, an example of how this might be applied? In the case of card shuffling. What's the probability so we're going to shuffle a deck of cards, and we're going to make it so that all possible orderings are equally likely. So in a deck of cards, there's 13 ranks, 4 suits, 52 cards. The ranks go ace, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then the face cards, jack, queen, and king. The suits, spades, hearts, diamonds, clubs. So there are 4 aces. And the question is, what is the probability that the 4 aces appear next to each other? In a well-shuffled deck. What I mean by well shuffled means that all orderings are equally likely. Well shuffled deck of 52 cards. Now this sounds, so in other words, we have 52 spots. And what are the events that I'm asking about? I'm asking about the event that we have ace, 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 ace in the first four, or ace, 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 ace in the second, third, fourth, and fifth, or the third, fourth, fifth, and sixth, and so on. So there's a few there's a few possibilities there. So I'm asking that they're just right next to each other, even though I've shuffled the deck that this happened, that they just so happen to appear. Well, the probability is going to be the probability of this event plus the probability of this event plus the probability of this event. We have to add up all those individual probabilities. But it's actually greatly simplified by realizing that the four aces next to each other is each one of these has exactly the same probability. So it's equal to probability that the four aces are all on top of the deck times how many different, so that each one of these has the same probability. And how many possible are there? Well, the first ace can appear in the first position, second position, third position, up to the 49th position, because there's 52 cards. So you would need, if the last four cards are aces, then it would be 49, 50, 51, and 52. There's 49 different ways for this to happen. They all have the same probability. And that probability is that the four aces are on the top. Okay. What's the probability that the four aces are on the top? Well, what's the problem? I have four aces. So how many options are there for the first position? I'm going to pick my four aces and I have to put them in order. So 4 fall 4. It's just 4 factorial. Divided by all possible choices of the first 4, which is 52 fall 4. That's how we would use exchangeability to our advantage. So important to distinguish with replacement, without replacement, independent draws, exchangeable draws. Exchangeable draws, there's some things that there's some similarities between exchangeable and independent, but they're definitely not the same. Some of the same concepts apply because we have a symmetry and we can use that symmetry to our advantage. And so it's important to recognize that symmetry when we have it and to use it accordingly and to use it appropriately.